Now, Ruchika, in force and motion, right, in this chapter, it is my recommendation would be that you take your time to correctly write down the forces or correctly establish the free body diagrams, correctly write the Newton's second law, F equals to ma. If you are dealing with the equilibrium situation, correctly write down summation fx equals to 0, summation fy equals to 0, summation fz equals to 0, and of course the summation of torques about, say, z-axis is 0, because we tend to deal with forces in 2 dimensions only at this stage. So which means that typically if x and y is your plane wherein you have the forces, then the torque about the z direction is the only relevant one. So trick is to write it patiently, make sure that you are not rushing through these questions. Okay. Beta, I'm reflecting back on the questions that I saw from Akash. And as I was thinking through it, the important thing is to perhaps do less, but do them patiently, do them with due diligence. No point in rushing. Okay. Because you unnecessarily get these questions, you miss out on something, and then you feel that makes a slight dent in your confidence, which does not help. Right? Chavi, I'm sure it's the same thing for you, Beta. Same advice will go for you as well in this chapter. Now,
Yes.
yeah, the JEE advanced practice questions, they are ready for this chapter. So I'm going to circulate them and make sure that you guys practice few questions. I'll try and give not more than maybe 2 per day, right? But there'll be those questions will make you think, right? They'll definitely make you think. They'll force you to improve your understanding of the situations. Okay. So we're going to start with number 2. I think we are done with number 1. Any questions from number 1? Let me just revisit number 1 that we did on last Thursday. So in this scenario, just as a quick recall, what we had was we had a particle or an extended rigid body like a rod in equilibrium with all sorts of forces acting, whether gravitational, normal force, there might be tension force, there might be your electric force, but not the frictional force. Why not the frictional force? Just to give the frictional forces some the due respect that they deserve, those scenarios have been segregated into other question types. But here, it's all about figuring out your summation fx equals to 0, summation fy equals to 0, and summation tau z equals to 0. And as far as the torque is concerned, just as a quick reminder, when we are talking about torques, the number of equations that you will get is still 1 in the z direction. So, for example, we had this scenario. So we had these scenarios where you had a rod with some mass placed somewhere, or it's hanging by some strings, and then some other mass at some different location, and then the mass of the rod is m. Let's say this is m1, this is m, this is m2. Now, when you write the torque, right? What is torque? Torque is the twisting action of the force. Something you will study more when we get to rotation. But there is no reason we cannot learn about torque now, because it's not that difficult. It's a very simple definition. Torque about a point, about an axis, is defined as R cross F. Torque is defined as R cross F. One of the most important things whenever we're talking about torque is torque about what point? Torque about what axis? That should be your first question that you should ask, even before you do anything else. Train your mind to think like that. So in this scenario, so when you try and figure out your torque about the z direction, so let's say this is my x, This is my Y, and Z is coming out of the screen. So if you try and figure out the torque due to all these tension forces and blah, blah, blah. So your question is, sir, about what point? Then my answer to that is you can pick any point. You can pick a point on the rod right here. You can pick this point. You can pick this point. You can pick the center of the rod. You can pick anywhere in this two-dimensional plane. You can pick any point, right? I can pick a point here. It does not really matter. You will still get only one equation. Okay, you will still get only one equation, one independent equation for tau z equals to 0. Okay, clear ना बेटा?
यस सर, मैं इस पे एक और क्वेश्चन कर सकते हैं क्या टॉक पे?
Okay. So let me see if we have 2021 question. So why don't we do this question? Let's do this question. And Beta Shridhar, I see a question. So, okay, Beta, you're not able to understand it. Is that because I'm talking in English? That's why you're not able to?
Good evening, sir.
Shridhar? Okay. Beta, in case you have any specific questions that you want to ask about equilibrium scenarios, so we're talking about Newton's laws of motion. If you have any questions that you want to ask, very specific questions about the topic, then please do write them down. I'll try and address them as soon as I get an opportunity. But I'll get back into the class. Manan Beta, welcome. Beta, we have started the Newton's laws of motion, the force and motion. So we are looking at the very first question type, which was a particle or a rigid or an extended rigid body in equilibrium with all sorts of forces, but not the frictional force. And you have to use sum of forces along x, y, and z, and the torque about z equals to 0 to figure out your the unknown. So please attempt this question. This is the question from 2021 JEE Advanced.
सर ये पहले कर रखे हैं.
You have done this one, Beta?
Yes, sir.
Okay. Just revisit it calmly, right? Just kind of write down, just draw things in your head. Think about the problem from different angle. Okay, still go ahead and practice it.
Yes.
So just to quickly recap, so we have this rod, so which is hinged at one end on the wall. In such question, the interest level is to understand the reaction forces at O. And in this case, we're also interested in the tension in the row. Reaction forces,
सर ABD आ रहा है.
B and D,
सर ABD.
A, B, D. Yes, beta?
Sir, ABDR.
ABDR. For students on YouTube, you might want to look at the torque about point P. That will give you the vertical component of the reactor.
Sir, I'm not really sure how to solve this.
Okay, beta. Because the rod is in equilibrium, so what do we have? If we take, let's say this is your x-axis. Let's say, beta, this is your x-axis. This is your y-axis. The z-axis will be coming out of the plane, right? Using the right-hand thumb rule. So if we, since the rod is in equilibrium, sum of all the forces acting on the rod along x must be 0, along y must be 0, and sum of all the torques about the z-axis. So what are the forces? Let me quickly draw them. So let's say there's this force. Let me call it FV. Let me call this FH. Let me call this W. This is tension T. This is alpha W, of course. Have I missed any other force, beta?
No, sir.
So now if you were to write summation Fy equals to 0, then you have, if I were to write it, right? So let's just see. So you will say Fv minus W minus alpha W. And let's say this angle, this is length L, and the rod is also of the length L. So this is angle is 45 degrees. So plus T cos 45 equals to 0. Summation f of x equals to 0. What does that give me? That gives me T cos of 45 minus f horizontal equals to 0. Okay. Which ones are the unknowns? You have Fe as the unknown, which is what we're trying to find. You have Fm, and of course the tension T. So we need one more equation, and that we'll get from the summation of all the torques about the desired points to be 0. Now, what points shall we take? I can take O, I can take P, I can take Q, I can take whatever I want. So let's say you take point P, about which you wanna. So now you have to figure out which one is more convenient, right? So why am I picking point P? Because I know the torque is R cross F, right? Torque due to force F, any force F is R cross F. In other words, its magnitude I can write as momentum into F. What is momentum? Let's say we're trying to find torque about this point. This is the line of the action of a force. This is the momentum, R perpendicular. So R perpendicular into F will be torque. And R perpendicular is the shortest distance from the point O on that line of action of force F. Right, beta? So if I calculate the torque about point P, it's very convenient because I am able to eliminate torque due to three forces altogether. Which three forces? The torque due to tension about this point P would be 0 because tension T is passing through that point. In other words, tension T is like this. So any force which is passing through O or the line of action of the force passing through O, the torque would be 0. Why? Because R perpendicular is 0. What was R perpendicular? The shortest distance from the point about which we're trying to find the torque, or about the axis about which we're trying to find the torque, on to the shortest distance between that point and the line of action, of course, which is 0 in this case. So the only forces that I'm left with for which I'll have torque is Fv and W. So if I were to write this about point P, what will I get? I'll get Fv into L, and that is in the minus direction because that's in the minus Z direction. Use the cross product, A cross B. We spoke about it, right? So this is the vector A, this is vector B. Their cross product would be like this, right hand thumb rule. So point your all your fingers in the direction of the A, right? And then curl your fingers towards B along the shorter angle, along the smaller angle. That means along this angle. Then your thumb should be pointed in the direction of the torque. Chavi beta, if there is anything that I need to provide more clarity on, so please do point that out right away, right? It's very important that we remove all doubts and confusion from the get-go, okay? So,
Sir,
yes, beta?
sir, what is exactly FP and FH?
Okay, so these are the reaction forces. These are the forces that the wall is applying, or that rather hinge the hinge at O is applying on the rod, right? We know it is the force is going to be somewhere in that direction, right? It might be like this, it might be like this, who knows? But it will have two components, one in the horizontal direction, one in the vertical direction. That's what these are. Fe and Fh are the reaction forces. That is the forces acted upon or acting on the rod by the hinge, by the wall. Is that clear?
Yes, sir.
Okay. And then you have the torque due to W, there will be W into L by 2. This will be 0. Okay. So what does that give us? That gives us Fv is W by 2. Okay. So it looks like it is independent of alpha. Okay. So that part is sorted. So A is correct. A is correct. Then it says the horizontal component of the reaction force at O is equal to W for alpha is equals to this. So let's figure out what is the value of Fh. So we have to figure out the value of Fh. Now for Fh, what I can do is I can either try and find the torques about point Q. Right? So I can use that. So I can write my torque. I could have actually done it this way as well, beta. Then I could have substituted Fv in this equation and found T. And once we know T, we know this Fh. Fh is T cos 45. And by the way, this Fv is sine 45, not cos. Yes, beta?
Yes, sir.
Or I could do it because I know from experience that if I were to talk about Q, this is Q, about point, then the T goes away, Fe goes away, and then I can quickly write it in terms of this one. So let's do that. So the torque about Q should be 0, which means Fh, that's direction of the torque is coming out of the screen, Z, minus W into the line of action is this, line of action of this for alpha W, perpendicular for this is this much, L by 2. So minus W L by 2 minus L alpha W equals to 0. Have I missed any other force? I don't think so, right, beta? So Fh is equals to Fh into L. Fh into L. So cancel out. So FH is W 1 by 2 plus alpha. If alpha is 0.5, if alpha is 0.5, then this is W, no? Plus 0.5, which is 1 by 2, that will be 1. So FH is, that is this. The last part is figuring out the tension. Tension, you can use this equation. So you can use T cos 45, or that means T is equals to FH, that is W into L by 2, into cos for divided by cos 45, that means root 2,
Into root 2.
right? Into root 2. Wonderful. So what does it say? The tension in the rope is 2W. Alpha is half. If alpha is half. Sorry, have I made a mistake here? I think I made a mistake. This is 2 alpha plus 1. So if alpha is 0.5, then this becomes 2. 2 divided by 2 is 1. W root 2. So not 2W, but root 2W. This is wrong. The rope breaks if alpha is greater than 1.5. Well, the maximum tension when the alpha is 1.5. When alpha is 1.5, then W becomes 2 root 2W. Right, Peter? Which is the maximum tension. So which means if alpha is greater than this, then we know T will further increase because alpha is in the numerator. If tension will go beyond this breaking point, then the rope will break. So even this is correct. All set?
Yes, sir.
Okay. So let me actually see if I can point out a good question for you guys to solve. While I'm figuring that question out, why don't you guys look at this question? This should be fairly easy, beta. Let's please go ahead and quickly solve this one.
So D option.
D option, okay. Ravi Manan,
सर मेरा एक कंपोनेंट आ गया दूसरा नहीं आ रहा.
okay. Ravi, beta, shall I solve the question or do you need another minute or so?
No, sir, you can go ahead.
So we have this pulleys of mass M. So first, let's step by step, let's establish the tension in this rope. What is the tension in this rope? Mg.
Yes, sir.
So, so if I just now let's draw the free body diagram of the pulley. This is my pulley. These are the some reaction forces. This force and this force. Let's say F vertical, F horizontal. These are the reaction forces acted upon by the clamp on the pulley, which is what we have to find out. Now, this is the small mg. Besides that, you have tension T. You have tension T. Let me call this center as O. So now, let's quickly balance out the forces. So if you look at the horizontal forces in the horizontal direction, so what will that give us? So in the horizontal direction, let's say I'm going to call this as x, positive x, this is positive y. So your FH is equals to T, is equals to capital Mg. Now let's balance out the forces in the vertical direction. FV is equals to Mg plus T, which means M plus M times G. So the net force exerted by the clamp on the pulley is square root of Fh squared plus Fv squared. So that's the magnitude of the net force. So G will come out square root of M plus M squared plus capital M squared. Ruchika beta, you said D.
Yes, sir.
Beta Manan, where were we stuck? Which component did you struggle with?
Sir, the horizontal one.
And beta, why did we struggle there? Just help me understand. Sorry, this is not that, sometimes teachers ask a sarcastic question. This is not a sarcastic question. I'm curious to understand how you were approaching. Chavi beta,
Yes, sir.
where were you stuck beta?
So I wasn't stuck. I was just a bit slow. I finished it.
That's fine. Don't worry. Even I'm slow. So, and slow is good. It avoids the errors. Now, Ruchika beta, torque about point O is balanced, no? Torque about O is 0, no? Yes?
Yes, sir.
Okay, good. Now, let's challenge you guys with a slightly another problem. So let's solve this question number 2, please. Hope you guys can read the question. Can you guys read the question? Heavy string है, mass m है. It's hanging between two fixed points A and B at the same level. The tangents to the string at A and B are at an angle theta with the horizontal as shown in the figure. The tension in the string at the lowest point is how much? Let me know if I should wait, beta, before if what I'm writing here is going to bother you. I'll not write it. But if you guys are solving it on your own, then I'll start scribbling here, which we can discuss later on. It'll just save us time.
Sir, mg by 2 tan theta.
mg by 210. Apna Manan beta, just watch what I'm doing and see if you disagree with something here. Would love to understand how you got mg by 2 tan theta beta.
Yes, this is same answer.
Okay.
Sir, tension at the midpoint निकालनी है.
Ah, you're right. So you're absolutely right. I found the tension T at the top. Ruchika, sorry, I forgot the question is asking here. Beta. Then this will be T. Let me call this as T dash, which is going to be horizontal. So T cos theta is T dash. Okay. Shall we beta clear?
Yes, sir.
Trying to find another worthy question. Okay, that's fine. Let's move to the next question type, beta. And do take a look at the anti-abhyas questions. Anti-abhyas questions tend to be fairly good as well. Let me see if there's anything with picture in it. Let's quickly this one. Chavi, I hope this is helping beta because you wanted to understand how to apply the torques and all, right? So let's do this one as well. Hopefully this will help. Assume these strings to be massless.
Three option.
Yes, sir.
Okay, good. Now we'll look at scenarios where you might be given for you might be given the potential energy function for a system. Okay, and you might be asked to determine the equilibrium position from that. Okay. So let's quickly revisit the definition of potential energy. How is the potential energy defined? Potential energy is defined as negative of work done by a conservative force. So once again, it is defined as change in potential energy is equals to, so du is equals to negative of work done by the conservative force. Work done by the conservative force. By the way, pay attention to this terminology when I say work done by the conservative force, and that's even the negative, right? So let's say if it was the gravitational force like mg, then it will be the work done by the negative of the work done by the gravitational force. That will be the change. Okay. As the particle moves by a small distance, let's say ds. What will be dw? Something that you will learn in the next chapter. Work done is defined as F force dot the displacement. Scalar product of force vector, net force on that. Or I shouldn't say net force. The force, the conservative force. So this is F is the conservative force, and ds is the displacement. So this is how we define du. So now, if I were to look at change in du with respect to certain direction, then let's say you are given u function, you're given some function u, and you are asked to determine the force. So from here, I know I can write del u by del s minus is force along that direction s. If you are given the potential energy function as a function of x, y, and z, then your force, which will be fx I cap plus fy j cap plus fz k cap, its x component will be differentiate u with respect to x only. Okay. And then substitute the values for x, y, z. And then fy is minus del u by del y. Fz is minus del u by del z. So if somebody says potential energy as a function of r is this much. Right? So what does this tell us? That if at any point, let's say r obviously is the position vector with respect to some origin, let's say O. So at this point P, this is my r vector, this is the distance r. So then U, which is a scalar quantity, once again, potential energy is a scalar quantity. It's scalar quantity. And if I were to differentiate U with respect to r, that means I'm trying to find out how does this energy vary if I move along the r direction by a small distance dr or del r. Let me use d instead of del because this might be slightly, it's very similar, right? It's very similar. So du by dr minus du by dr will be the force along the r direction. What will be the force along, let's say, this direction? I'm going to call it f theta. Well, that'll be 0 because there is no change in the u. There is for all r, if I move in this direction tangentially, then there is no change in u. That means del u by del theta or del u by del s, this along the tangent would be 0. So the force is only in this direction. Okay. I hope what I said there made sense. So this is my force. How you find the force? Once you have the force, which is minus del u by del r, then they're saying determine the equilibrium position. What do we understand by the equilibrium position? Now we have talked about the equilibrium scenarios, and in the equilibrium scenario, the net forces are 0. Right? Net forces are 0. So if you were to equate this to 0, then you will be able to find the value of r for which the force is 0. Okay, the force is 0. What does that give us? That'll give you the equilibrium position. So let's do one problem and that'll make a little bit more sense. So let's look at this scenario. Right? It says potential energy as a function of r is given by a by r to the power 10 minus b by r to the power 5, where r is the interatomic distance. Between the interatomic means distance between the nuclei, between the center of the two nuclei or atoms. A and B are positive constant. And what is the equilibrium distance between the two atoms? Right. First, we're going to find out. Let's say this is my A, this is my B. R is the intraatomic distance, right? This is the R. So if you change R, if you put B here, if you move B here, right? So how does it change? So let's find that out. So let's keep A steady. Let's keep it fixed at the origin O. Now, if you move B slightly away or closer to O or the other atom other atom A, then how will my potential energy vary? So let's find it out. So du by dr, and I'm going to put minus sign there, will give us minus. Derivative of this will be, what will this be, beta? Can somebody tell me, please? Is this correct, what I'm writing here, beta?
Yes, sir.
Okay. So now if we equate, so this is my force. Now, when they reach the equilibrium position, right? What is their equilibrium position? Where the repulsive forces of the electrons are balanced by the attractive forces between the nuclei and the electrons, the electron cloud. So when the two balance out, the net force on these nuclei, on the atoms, would be zero. So let's figure out what is the net force when the net force between the two will be zero. So if I equate this to zero, so that'll give me 10A 5B r to the power 6. In other words, r to the power 5 is 2 A by B, and I'm going to take the power 5 and take the inverse of that. That means take the power 1 by 5. So this is my distance at which the force between the two is zero. So that must be the equilibrium distance between the two atoms. Clear? Yes, Peter?
Yes, sir.
Okay, good. So we'll do just one more problem of this and then we'll move on, because the rest is pretty much the same. From 2021. So it says the potential energy U of a diatomic molecule is a function dependent on R, as U is equals to this, where alpha and beta are positive constant. The equilibrium distance between the two atoms will be this much, where A is 1. Now, for the students on YouTube, what I would recommend is you look at the website and make sure that you solve more problems of the same, right? So it's all about honing the skill one day at a time, right? One day at a time, you're learning to practice different types of questions. And don't forget to practice the JEE Advanced questions sometimes, or the JEE Advanced practice questions. So those questions will challenge you. So you can obviously solve the previous year questions, which is what we are doing. And you can solve some fresh ones as well, some newer ones as well. But they will definitely force you to take a very close look at your concepts. Okay. And if you have any doubts, then you can always ping me here, or you can chat me up on our website. The link for the website will
Sir, I'm getting A by B
be
is 1 by 5.
description.
So A is equals to 1.
Sorry, Beta, what is it?
Sir, A is equals to 1.
A is equals to 1. Okay. And what is B, by the way?
So 5.
So 5.
Okay. It's a very similar problem. It's pretty much the same problem. No?
Yes, sir.
Yeah. Okay. So let's move on. So now we'll look at scenarios wherein the body, or I should, in fact, when I talk about the body, I should talk about whether we're talking about a particle or an extended rigid body. What's the difference between a particle and rigid body? So particle is where the dimensions of the object are fairly small compared to the other dimensions. Okay, so you don't need to worry about how things are varying along its own dimensions, right? So then there'll be a particle. But if the dimensions are significant enough where things are not uniform with the, let's say, the force acting on it, the force is not uniformly spread along the rod, right? So then that's what we'll refer to as an extended rigid body. And what do we mean by a rigid body? Rigid body is one where the distance between the atoms or the molecules or between different sections of the body do not change with time, right? Their internal distances do not change with time. Okay, so now we'll look at the scenario 1 and we'll also talk about the scenario 2. So let me quickly read through here. It says, in the scenario A, one or more masses are being pushed against a vertical wall, meaning an external horizontal force is pressing these masses against the wall, which will result in equal and opposite normal force between the masses and the mass and the wall. And as gravity tries to pull them down. Okay, there will be tendency to slide and a frictional force will come into play. Note that since there is no actual sliding rather than only the tendency to slide, the frictional force will be static frictional force, which can have any value between 0 and mu n, something we have discussed in the previous class as well. But if it involves about to slip situation, then that means that the static frictional force has reached its maximum value of mu n. Then it says use force and torque balance equations to determine the unknown. Now this is an interesting scenario, the one in the A. So just kind of closely look at this scenario. So what do we have? We have a cubical block, right? A cubical block with force F acting along a line of force. The line of action of force F is passing through the center of the cubical block, and there is a frictional force between the wall and the block. Let's say the frictional coefficient of friction is mu. And we are not suggesting it's about to slip, right? Let's say that the mass of the cubical block is m. Right? So then the first question is the normal force, that means the force being applied by the wall, is it uniformly distributed or is it non-uniformly distributed?
So non-uniform.
Non-uniformly distributed. And can you prove that, Peter? That the normal force exerted by the wall on the cubical block will be spread non-uniformly along the side of the block. How would you prove that?
So talk about the center of mass should be 0.
Okay. So torque about O should be 0.
Yes.
Now the moment arm for F is 0 anyway. So this is 0 times F. What about the frictional force? It must be acting in this way. Why do I say that? Well, the frictional force F must be equal. If you do balance of forces along the y direction, which is the vertical direction, then you will get F is equals to mg. Correct, Namita? Yes?
Yes.
Okay. So now, the torque due to F would be in the minus z direction, which is going into the plane, and there will be F times A by 2. Okay. Now, if the normal force was uniformly distributed, then the net force can be thought of being of acting at the center, right? So in which case the equation will not be balanced. So if this were the normal force acting at the line of action is passing through the center, which will be the scenario if normal force is uniformly distributed. In that case, this is the equation that you will get. But how can this be 0? This cannot be 0. So where do we need to fix our issue? Well, line of action of force F is clear. So all that means is, all it indicates is actually the normal force is not passing through the center. The effective normal force is actually passing through somewhere over here. Okay? Shall we beta clear? Now the normal force is trying to rotate it like this. About good. While the frictional force is trying to rotate it like this. So now they will cancel each other's torque. Is that clear, beta? Chavi?
Yes, sir.
Okay. On the scale of 1 to 5, are we absolutely clear or we have some clarity but doubtful?
So like 4.
4, okay. Okay. Now, let's talk about the scenario B. In scenario B, what we have is we have two masses M1 and M2 placed one on top of each other. And the frictional force between the two is mu1, or coefficient of friction is mu1 between the two masses. And between M2 and the ground, it is mu2, right? And let's say you have force F acting on this one. So question is, what is the maximum force that you can apply? What is the maximum force that you can apply such that the two masses, such that the system is still in equilibrium? How would you determine that? So what is the maximum force that you can apply such that the two masses are still stationary? Yes, Peter? Any ideas? So let's think of the tension T acting, tension T in the string is, the tension in the string is T. So we have, let's now write down the, or draw the rigid body diagram for the two masses independently. So here is my M1. Normal force is acting this way, N1. This is M1G. Frictional force is, now if the bottom one moves to the left, the right one has to move to the right, right? So the two surfaces are sliding, gliding against each other. So the frictional force would be acting in this direction. Okay, and this is the direction of the tension T. Let me draw something similar for M2. So M2, we have N1 acting downwards, and obviously we have M2G acting downwards, and the ground is applying a force N2. This is the force F, and this is the force F1, and then there is another force F2, the frictional force between the ground and M2. Yes, Peter?
Yes, sir.
Okay, so now the about to slip situation in this scenario would be T is equals to, by the way, T is equals to F1. In the about to slip situation, it will be, tension would be mu times N1, which is M1G. Okay. Now, let's look at the second mass. So if we do the force balance, so what do we have? So we have F is equals to F1 plus F2, and of course we have tension T in this direction as well. So T plus F1 plus F2. So what do we get? So tension T plus mu1 M1G plus mu2 m1 plus m2. Okay. Or rather, I should have written F1 and F2. So now question is, which frictional force will reach the limiting condition first? So can we quickly figure out if you knew mu1 and mu2? So I should not write it like this. Correct? So this I can write as 2F1 plus F2. So let's see if we can see an actual problem, and then we should be able to solve or get a better perspective on this one. Let me quickly try and find it. By the way, this is the question we looked at. Yeah, I think this is what it is. Oh, this seems to be simpler. Anyway, let me see. This is actually quite a good problem. This is also a good problem. Let's start with this one. But today we'll only do this problem and then we'll carry on our practice tomorrow. Please go.
Sir, I've done this one before.
You have done this one before?
Yes, sir.
Let's find something different. Let's solve this one. Yes, madam?
So would it be D?
Yes.
Yeah. They're very strange choices, by the way. What about the, can it be zero? The friction force on B due to A?
No, sir.
Why will that be, better?
Sir, because the surfaces are rough. Sir, but when they're falling, then it will be zero.
Correct. And they have to fall because they cannot remain in equilibrium. There's only, if both are falling with the same gravitational acceleration, then there is no tendency to slide. if both the masses start to fall with the gravitational acceleration g, because after all this force mg, right, in the vertical
Sir,
direction. Yes, Peter?
sir, do you think they might be asking us ki like A and B should be in equilibrium with respect to each other?
No, Peter, no. Equilibrium means the system is stationary, is not accelerating. With respect to each other, that would be very complex language, and they have to be specifying that. Now, can
Yes.
somebody prove that there cannot be any friction force between the two here? Just logic. Just assume that there is some friction force. B is applying on downwards in the acceleration on the A, and the other one is applying the upward direction. And very quickly you will see that as soon as you assume that, then the accelerations would be in the opposite direction, which means that the friction force has to reverse direction. That's the only way you will be able to satisfy is when the friction force between the A and B is zero. I can always say, hey, both are falling with the gravitational acceleration, so there will be no force. But if you still want to prove yourself the same using equations, you can assume that there is some friction force between the two, assume some direction, and then your acceleration will prove that your chosen direction is wrong. Right? But if you choose it the other way around, again it will say it's wrong. Why it's wrong? Because it has to be zero, otherwise it will create the equations cannot satisfy. Yes, no? So let me explain what I mean. So let's say there is a frictional force. So on B, it is acting in this direction. On A, this is acting in this direction, right? So what does this mean? That the acceleration of A is less than G. Correct, no? And what does this mean? The acceleration of B is greater than G. Correct, no, Manan? Now, acceleration of B is greater than G, which means acceleration, this B is going to move faster, right? Which means that A will try and hold it back. So the frictional force on B should actually be in this direction because B is trying to slide downwards relative to A. Yes? Then the assumed directions are wrong then. But if you assume them the other way around, again, you will come to the same conclusion that it's wrong. If it didn't make sense, don't worry. Okay? If it did, good. Let's quickly check what is the answer that they have given. Well, it's kind of a shame. The frictional force will be zero as well. In any case, but I will take the break here today and we'll resume the class tomorrow. Same time. Any questions before we leave?
No, sir.
Okay. Alrighty, Peter. Take care. See you tomorrow.
Thank you, sir.
Bye, Peter.